Innovations and Inventions, Radar Technology. Welcome to History Explained, where we illuminate the past to better understand our present. I'm your guide to your daily journey through the past to empower the future. Today is Sunday, July 13, 2025. As we do every Sunday, we're exploring a revolutionary innovation that fundamentally changed how humans interact with their environment and shape the modern world. Today, we turn our attention to radar technology, one of the most crucial innovations of the 20th century that transformed military strategy, aviation safety, weather forecasting, and space exploration. Developed in the years leading up to World War II, radar provided the ability to detect objects at great distances using radio waves, fundamentally altering warfare and civilian applications. What makes radar particularly remarkable is how it emerged from theoretical physics research to become an essential technology that saved countless lives during World War II while laying the foundation for modern air traffic control, meteorology, and space exploration. This innovation demonstrates how scientific breakthroughs can have immediate practical applications with far-reaching consequences. So let's explore the development of this transformative technology, examining its scientific foundations, the wartime innovations that perfected it, its crucial role in major military operations, and its lasting impact on both military and civilian life. The scientific foundations of radar can be traced to the late 19th century when Heinrich Hertz demonstrated the existence of radio waves and showed that they could be reflected by solid objects. However, the practical application of this principle for detection purposes would not emerge for several decades. The theoretical possibility of using radio waves for detection was first suggested in 1886 by Heinrich Hertz himself, but the technology to implement such a system did not exist. Early radio equipment lacked the precision and power necessary to detect reflections from distant objects reliably. The first practical demonstration of radio detection occurred in 1904 when German inventor Christian Holzmeier developed the telemobiloscope, designed to prevent ship collisions in fog. While his device could detect ships at short ranges, it failed to gain commercial acceptance due to its limited capabilities and high cost. Serious development of radio detection systems began in the 1930s as military leaders recognized the growing threat posed by aircraft. The increasing speed and range of military aircraft made traditional visual observation inadequate for air defense, creating urgent need for early warning systems. British scientist Robert Watson Watt is often credited with developing the first practical radar system. In 1935, he demonstrated that radio waves could detect aircraft at distances of several miles, proving the concept's military viability. His work led to the rapid development of Britain's chain-home radar network. The British government, recognizing radar's potential importance for air defense, invested heavily in the technology's development. By 1939, a chain of radar stations along Britain's coast could detect approaching aircraft at ranges up to 100 miles, providing crucial early warning of enemy attacks. Meanwhile, other nations were developing their own radar systems. Germany had working radar technology by the late 1930s, though they initially focused more on naval applications. The United States also began radar development, with significant contributions from the Naval Research Laboratory and private companies. The outbreak of World War II accelerated radar development dramatically. The technology's importance became clear during the Battle of Britain, when British radar operators provided early warning of German air attacks, allowing RAF fighters to intercept enemy formations before they reached their targets. The British chain-home system proved its worth repeatedly during 1940, enabling effective deployment of limited fighter resources against much larger German formations. Without radar warning, the RAF would have been forced to maintain continuous air patrols, quickly exhausting their pilots and aircraft. American entry into the war brought vast resources to radar development. The MIT Radiation Laboratory, established in 1940, became the world's leading radar research center, developing numerous innovations including microwave radar systems that provided much greater accuracy and resolution. The development of cavity magnetron technology by British scientists John Randall and Harry Boot revolutionized radar capabilities. This device could generate high-power microwave signals, enabling radar systems with much better resolution and range than previous technologies. Microwave radar systems could detect smaller objects at greater distances while providing more precise location information. This technology proved crucial for naval operations, where accurate detection of submarines and surface vessels could determine battle outcomes. Radar technology evolved rapidly throughout the war, with increasingly sophisticated systems developed for specific applications. Air-to-surface radar enabled accurate bombing through clouds and darkness, while airborne intercept radar allowed night fighters to locate enemy aircraft in complete darkness. Naval radar systems became essential for fleet operations, providing early warning of enemy ships and aircraft while enabling accurate gunfire control. The ability to fight effectively in poor visibility conditions gave radar-equipped forces significant advantages over opponents relying on visual observation. The technology also proved crucial for submarine warfare. Radar-equipped aircraft could detect surfaced submarines at considerable distances, making it increasingly dangerous for U-boats to operate on the surface. This capability significantly reduced the effectiveness of German submarine campaigns. Ground-based radar systems provided air defense for military installations in cities, while mobile radar units supported ground forces by detecting enemy aircraft and directing friendly fighters to intercept threats. These applications demonstrated radar's versatility across all branches of military service. Perhaps most importantly, radar enabled new tactical approaches that revolutionized warfare. Night bombing became practical with radar navigation and targeting systems, while naval battles could be fought in complete darkness using radar-directed gunfire. The D-Day landings demonstrated radar's importance for complex military operations. Allied radar systems provided navigation assistance for the invasion fleet, detected German aircraft attempting to attack the landing forces, and guided Allied fighters to intercept enemy threats. In the Pacific theater, radar proved equally valuable for detecting Japanese aircraft during major battles like Midway and Guadalcanal. The ability to provide early warning of air attacks allowed Allied forces to prepare defenses and launch interceptor aircraft effectively. The development of radar countermeasures also became important as the war progressed. Both sides developed technologies to jam enemy radar or create false signals, leading to an electronic warfare arms race that continues today. Post-war applications of radar technology expanded rapidly into civilian uses. Air traffic control systems adopted radar to track aircraft safely, revolutionizing commercial aviation by enabling flights in poor weather conditions and reducing collision risks significantly. Weather radar became essential for meteorology, allowing forecasters to track storm systems and provide accurate warnings of severe weather. This capability has saved countless lives by enabling early warning of hurricanes, tornadoes, and other dangerous weather phenomena. Maritime navigation was transformed by radar technology, with merchant ships and fishing vessels using radar to navigate safely in fog and darkness. Collision avoidance systems based on radar became standard equipment for ocean-going vessels. The space age brought new applications for radar technology. Ground-based radar systems tracked satellites and spacecraft, while radar altimeters enabled precise landing systems for aircraft and spacecraft. Deep space radar provided information about planets and asteroids throughout the solar system. Medical applications emerged with the development of imaging systems that use radar principles. While not using radio waves directly, technologies like ultrasound and MRI employ similar concepts of wave reflection and interference to create detailed images of internal body structures. Modern radar systems are far more sophisticated than their World War II predecessors, using digital signal processing and computer analysis to extract detailed information from radar returns. These systems can track hundreds of targets simultaneously while providing precise position and velocity information. Phased array radar represents one of the most advanced developments, using electronically steered antenna arrays that can track multiple targets and perform multiple functions simultaneously. These systems are used for air defense, space tracking, and weather monitoring applications. Stealth technology has created new challenges for radar systems, leading to development of more sensitive equipment and new detection techniques. The ongoing competition between stealth technology and radar capabilities drives continued innovation in both fields. Synthetic aperture radar, SAR, enables high-resolution imaging from aircraft and satellites, providing detailed maps of terrain and monitoring changes in land use, ice coverage, and other environmental factors. This technology supports both military reconnaissance and environmental monitoring. Ground-penetrating radar has found applications in archaeology, geology, and engineering, allowing researchers to map subsurface features without excavation. This technology has revealed buried structures, detected underground utilities, and located geological formations. Automotive radar systems are becoming increasingly common, providing collision avoidance and adaptive cruise control capabilities. These systems represent the latest evolution of radar technology into everyday consumer applications. The future of radar technology includes integration with artificial intelligence and machine learning systems that can automatically identify and classify detected objects. These developments promise to enhance radar capabilities while reducing the need for human operators. Quantum radar represents a potential revolutionary development, using quantum entanglement principles to create detection systems that could potentially overcome stealth technology. While still experimental, this technology demonstrates radar's continuing evolution. Climate monitoring increasingly relies on radar systems to track changes in ice sheets, forest coverage, and ocean conditions. These applications highlight radar's importance for understanding and addressing environmental challenges. Space exploration continues to benefit from radar technology, with planetary radar systems mapping the surfaces of Venus, Mars, and other planets, while asteroid tracking radar helps protect Earth from potential impacts. The development of radar technology illustrates how wartime necessity can accelerate scientific innovation with lasting civilian benefits. The same technology that helped win World War II now protects aircraft passengers, warns of severe weather, and supports space exploration. Radar also demonstrates the importance of international scientific cooperation, as researchers from multiple countries contributed to its development and applications. The sharing of knowledge and techniques has enhanced radar capabilities while promoting peaceful uses of the technology. Modern society depends on radar technology in ways that are often invisible to the general public. From the air traffic control systems that manage commercial flights to the weather radar that provides storm warnings, this World War II innovation continues to protect and serve humanity. Radar technology stands as one of the 20th century's most transformative innovations, evolving from a wartime necessity to an essential component of modern life. Its development demonstrates how scientific research can produce practical solutions to urgent problems while creating lasting benefits for society. The story of radar reminds us that technological innovations often have consequences far beyond their original intended applications, with military technologies frequently finding peaceful uses that benefit all humanity. Thank you for joining us for this exploration of radar technology's development and impact. Next week, we'll be back with our This Day in History episode examining the significant events that occurred on July 14th throughout history. If you enjoyed this journey through history, please like this video, subscribe to our channel, and hit the notification bell. What aspects of radar technology do you find most impressive or important for modern life? Let us know in the comments below. Until next time, I'm your guide for History Explained, where we believe that understanding yesterday is the key to navigating tomorrow.